Okay, friends, welcome back to nuclear chemistry. Today, we're going to be focusing on the concept of half-life. And what half-life is, if you look at the definition, is it's the amount of time it takes for half of a sample of a radioactive isotope to decay. And a relationship between half-life and nuclear stability is the shorter the half-life, the more unstable a nucleus is. So isotopes that have really short half-lives have pretty unstable nuclei versus ones that have longer half-lives have pretty stable nuclei. And remember, you can get some half-life information as well as decay mode on reference table N. And I think this does a really good job of linking what we talked about in the first lesson of nuclear chemistry to now. If you take a look at the first isotope listed on reference table N, it's gold-198. Gold-198 has a pretty short half-life, 2.69 days. Right, so it has a pretty unstable nucleus as compared to something like carbon-14 that has a half-life of 5,730 years. So if you had 100 grams of the isotope of gold-198, after 2.69 days, only 50 grams of it would still be gold-198. The other 50 grams would have decayed and become something else. You can actually figure out what it might become by looking at decay equations. So we've already done something like this, whereas gold-198 is a beta emitter. So its decay mode is beta. That means it's going to give off beta particles when it decays, which is right here in the equation, and it's going to become a more stable 19880 Hg, so mercury. And again, after 2.69 days, half of the sample of gold-198 will have decayed and become something else. Okay, and obviously it would take a lot longer for 100 grams of carbon-14 to become 50 grams of something else because it's got such a larger half-life, it's got a more stable nucleus. So if you take a look at some half-life problems, and of course we need to have reference table N handy in case we need to get information from there. The very first one is talking about the isotope chromium-51. It has a half-life of 28 days. It's pretty important. I'm going to underline that. And it wants to know the fraction. Again, remember, we want to circle or put a box around what it is that we want to find. Of the sample of CR51 will remain after 168 days. Okay? Well, one way of attacking half-life problems is by simply making a chart. So this is a technique that I've always used. And I always label the three columns the same way. This first column is half-life periods. And that's just simply going to be 0, 1, 2, 3, 4, however many half-life periods go by. The middle column is time, and the last column is mass. Now, this particular question does not give us an initial mass, so I can actually leave that blank to start. But because of the information, I know that one half-life period has a length of 28 days, basically. So every one half-life, 28 days will have gone by. And every time a half-life goes by, I'm going to be left with half the mass that I started with. So after two half-life periods, 28 plus 28 gives me 56. So 56 days would have gone by, and 1/2 of 1/2 is 1/4. And I'll continue doing this. After three half-life periods, 56 plus 28 gives me 84. 84 days have gone by, and 1/2 of 1/4 is 1/8. And you might be asking yourself, well, how long do I have to keep this chart going? Well, look back at the problem. Wants to know what fraction remains after 168 days. So I have to keep doing this until I get to 168 days. Not a problem, okay? After four half-life periods, now we're up to 112 days, and half of 1/8 is 1/16. After five half-life periods, we're now at 140 days, and that 1/16 becomes 1/32. And guess what? This last one, after six half-life periods, we're at that value in the problem, 168 days, and that means my answer would be the fraction that remains is 1/64. Okay, and there's my answer. There's the fraction that remains after that amount of time. But I want to show you another technique that you can use. You don't have to always set up this chart. Okay, there's another technique where you can actually just kind of use a little arrow system. And how it's going to look is you have some kind of starting mass. All right. Now again, it doesn't give me my starting mass. So if it gave me 100 grams, I start with 100 grams. But after every half-life period, you're going to end up with half of what you had. So if I had 100 grams to start over here, where this 1/2 would be 50 grams. Okay. But again, this is asking us for fractions, so we can actually just keep going this way. So every time I draw an arrow, I keep taking a half. Okay, so I put time. I put the time elapsed over here on the arrow, and I keep doing this 1/8, and over here would be 1/12, and that'd be 1/16. Okay, and another half-life would go by, which gives me 140, okay, and that'd be 1/32, and I've run out of room, so I'll do here at the bottom here, and then one more half-life goes by, and that would be my 168, and there's my answer, 1/64. I'll show you both techniques for the next problem, okay? But the next problem's a little different, because here it gives me the mass. How much of a 40-gram sample of cobalt-60 will remain unchanged after 15.78 years after it begins to decay? Okay. Now the problem here is it doesn't give me a half-life, but it does give me a radioactive isotope. So what I'm going to need to do is go back to reference table N, and sure enough, here's cobalt-60, and there's its half-life right there. Okay, cobalt-60 is right there, and there's its half-life of 5.26 years. So going back to it, I know I can set up my chart, which I'm very comfortable doing, and I'll show you with the arrow method as well. And I've got my half-life periods, time, and mass. And again, I start off with 0 time having elapsed, and in this case I have an initial mass of 40. After one half-life period, that value that I got from reference table N, 5.26 years would have elapsed, and of that 40 grams, only 20 would remain as cobalt-60. So I keep taking half there. After 2 half-life periods, 5.26 times 2, or if I just keep adding 5.26, becomes 10.52 years. And of that 20 grams, only 10 grams would remain. And after 3 half-life periods, that 10.52, I have to add 5.26 to it again. That's 15.78. Okay, that's pretty significant because that's what it asked for in the problem. Would now become 5.0 grams. And there's my answer. That's the amount that would be left. Okay. So if you like that arrow method, I'll show you that one as well. You would start with 40 grams. Okay, so I start with 40 grams. And after one half-life, that means 5.26 years have gone by. That 40 would become 20. And after another half-life, 10.52 years would have gone by, and that 20 would have become 10. And one more arrow, okay, because I'm running out of room here, would mean that I have 15.78 years would have gone by, and that 10 would become 5 grams. So either way, either system, whether you like the chart system or the arrow system, either one works effectively to figure out how much of a sample you would have left after a certain amount of time. Okay, let's do one more. Next one in the note packet. Now this one's different too because this time it's going to ask me for the mass of the original sample. So now if you take a look at it, it says after 49.44 hours, okay, 5 grams of a sample of potassium-42 remain. What was the mass of the original sample? Now in this particular case, I think the chart really works well here. Okay, you could do it the other way, and I'll show you how that works as well. But I know that I'm going to have my half-life periods, time, and mass. And of course, I've always got to start out with 0, 0. And here's the problem. I don't have an initial starting point. Well, that's okay, because if I know the half-life of K42, I can figure this out. Again, where am I going to go for this? I go for this right here on reference table N. Here's K42 right down here on the bottom. K42, and it has a half-life of 12.4 hours. So this one's probably got the most unstable nuclei of all the ones that we've talked about so far because it's got a pretty short half-life, okay, 12.4 hours versus years or days that we've seen before that. So 12.4, that 12.4 hours is my half-life, okay? So I know that after one half-life period, 12.4 hours would have gone by. Now, I know I would have half of the mass left, but I don't know how much I started with. That's okay. After 2 half-life periods, that 12.4 becomes 24.8 hours. And after 3 half-lives, that 24.8 would become 37.2 hours. So I'm just continually adding 12.4 hours to it. And after 4 half-lives, I get 49.44 hours, okay? And that's important because that's what it says in the question. Okay, how after 49.44 hours. So now I've got this, right? And I know it's taken 4 half-lives, but there's another piece of information. It says at this point, 5 grams remain. So now, instead of taking half in this column like I normally do, I'm going to start doubling it to get to that original mass. So after 3 half-lives, I would have had double that, which would have been 10. And after 2 half-lives, I would have had 20. After 1 half-life, I would have had 40. So my initial mass would have been 80. And there's my answer. Okay? So in this case, I would just have to work backwards to figure that out. Now, how would you do this using the arrow method? Well, you'd have to kind of figure out the first step. So if you know that 49.44 hours have gone by, and if I divided that by the half-life of this, I'm going to get about 4 half-life periods. Okay, so now if I know that it's going to be about 4 half-life periods, I can work backwards and figure that out, knowing that I'm going to end with 5 grams. I know that the half-life before that would have been 10 grams. The half-life before that would have been 20 grams. The half-life before that would have been 40 grams. And my one more half-life, because that's only 3 of them, would then be 80 grams. So 80.0 grams. Either way, so you just have to do a little extra step with it. You have to figure out how many half-life periods you'd have when you're looking for the original sample. I personally prefer the chart method because you can use it for any half-life problem that you're going to get, but I wanted to show you that there's 2 ways of doing this. So that's it for half-life, and what I'd like you to try to do is some half-life practice problems, and I'll be around to help. Thanks, guys.